Welcome to Dataless U. I'm Paul, coming to you from Brooklyn. Today we're going to take a look at synthetic division. All right, we're going to take a look at a fourth degree polynomial and see what we can figure out. So let's get started. I've already got the function up here on the big board. I'll read it out loud. f of x equals x to the fourth minus 11x cubed plus 43x squared minus 69x plus 36. So today, in short, we're going to take a look at a number of different ways of sort of figuring out this equation, what it looks like, what its roots are. We're going to look at the sum of the roots, the product of the roots, the rational root theorem, and then finally we will do some synthetic division. So first of all, we should have a general picture of this curve in our minds. It's a fourth degree equation, so it's an even degree equation. So it's going to open up in either direction. Now, why up and not down? So it's going to open up because the coefficient for x to the fourth is positive. It's just 1. And so we're going to open up as we move to the positive infinity for x, and we're going to open up as we move leftwards to the negative infinity for x. In fact, it's going to look like a W. Fourth degree equations generally look like W's. What else do we know? Well, it's fourth degree, so it has 4 roots. And really, that's our focus today. We're going to look for those 4 roots. So how do we go about doing so? Well, first we can make some predictions or some generalizations about the roots. The sum of the roots is equal to negative a sub n minus 1 over a sub n. Now, what are those a's? Those a's are just the coefficients, so I'm going to go ahead and draw them here. This missing 1 here is a sub n. This 11, negative 11, is a sub n minus 1. And this would be, the 43 would be a sub n minus 2, and so forth. So a just stands for a constant or a coefficient, and then here, our constant 36 at the end is a sub 0. Let's make sure we can see that, 0. Okay, so that means that the sum of the roots for this equation is negative. A sub n minus 1, we said was negative 11. Divided by a sub n is 1, which is going to simplify things for us here today. And so the sum of the roots is 11. Okay, interesting, good to know. Let's take a look at the product of the roots. Product of the roots is a simple and elegant formula. It's a sub 0, which was the constant at the end, 36, divided by a sub n, which we know is just the 1. So again, 36. Okay, so we know the sum of the roots is 11. We know the product of the roots is 36. As we find the roots, or when we find the roots, we'll come back and we'll take a look and see if we've confirmed numbers 1 and 2 here. So, rational root theorem, as usual today, we are working out of Richard G. Brown's Advanced Mathematics textbook. So if you want to take a look at the rational root theorem and follow along at home, it shows up on page 82. In short, the theorem reads that if you have a function, and notice that the notation here is similar to what I've written above, p of x equals a sub n times x to the nth power plus a sub n minus 1 times x to the n minus 1 power, and so on and so forth, all the way out to your constant a sub 0. And I'm going to read out of the text, and then we're going to kind of decode this language. If one of the roots of the equation p of x equals 0 is x equal to p over q, where p and q are non-zero integers with no common factor other than 1, then p must be a factor of a sub n, a sub o, and q must be a factor of a sub n. So what does all that gibberish mean? It basically just means, as I've written here, that the possible rational roots of this function are equal to the factors of a sub n. Well, our a sub n, our a sub 0 was 36. So what are the factors of 36? I'm just going to write them here. 1 and 2 and 3 and 4. Then we jump to 9 and 12 and 18, and of course 36 itself. And over the factors of a sub n, which is just our one coefficient, again making things simple for us today. So basically all of these are possible roots, and it's plus and minus all of them. And so I'll write it here again, equals all of these are possible roots, plus and minus 1, and the plus and minus goes for all of these. Plus or minus 2, plus or minus 3, and so forth, all the way out to our plus or minus 36. Those are our possible roots. So as we begin now our synthetic division, those are the numbers we're going to try. Okay, so synthetic division shows up in the textbook on page 58. You can turn there now and take a look. Essentially what you do is you take the coefficients of your function. It's easy enough. See, we have the 1, so we're going to write 1. We have the negative 11, we'll write negative 11. We have the 43, and you write out all your coefficients. We have the negative 69, and we have the positive 36. Okay, and then what we're going to do is we're going to put a number into there. Let's put it up here. We're going to put, let's try our first possible factor, right? So let's use a different color here for our synthetic division. Let's try positive 1, right? If we put 1 in, here's how it works. You want to draw a line here. This first number you just bring down, and then really what we do is we multiply going up, right? Multiply, which is 1, and we write that number here. All right, and then we add going down, so we add. And we're going to do this in each column. So negative 11 and 1, negative 10. We're going to multiply again, get negative 10. We're going to add going down, we have positive 33. Multiply again, positive 33. Add going down, negative 36. Multiply, negative 36. And add going down. And we get a 0 here. Yay! That's what we wanted. We want a 0 there. In short, if our remainder is 0, then we've proven that 1 is a root for the function. Now what does that mean? A root here means an x-intercept. It's where the graph is going to cross the x-axis, and we'll look at that in a moment. A root means that when we set this equation equal to 0, x of 1 will make that equation true. So roots mean zeros and intercepts and solutions to the equation. And that's really our goal here today, to find all of those roots. Now, what does this synthetic division mean? I just want to kind of point out that what we've really discovered here is that if we take, right, this original big long function, right, minus 11 x to the third plus 43 x squared, and we'll call this the this is the quotient, right? The dividend, sorry. This is called the dividend. And essentially, we're just dividing it, right? We could show it even in long division here. We're dividing it by this x minus 1, right? So that's the divisor. I think it's key that you kind of see the inner working of synthetic division. It's really just regular old division. And then these numbers here, this is sort of the point here of showing this. These numbers here, the result, they're the coefficients for the quotient. And the quotient you would write here. So we get x to the third minus 10x squared plus 33x minus 36. All right, and so again, that's called the quotient. Quotient. And that's important because then moving forward, as we do more synthetic division, we can just use those numbers from the quotient. We can use those coefficients. So let's go ahead and do so. It's 1, negative 10, 33, and negative 36. So we'll write those here. 1, negative 10, 33, and negative 36. So let's try another number. Remember from our rational root theorem, 2 was maybe a possibility. All right? And we'll go ahead and try 2. We'll do it the old-fashioned way here. Bring the 1 down. All right, multiply, add. Negative 8, right? multiply, that's negative 16, add, that's positive 17, multiply, positive 34, add, we get negative 2. Oh no! If you get, it looks a little drastic. If you get a number that is not 0, well then that doesn't work. Okay, so basically what we've just proven is that 2 is not a factor of this function. And the reason I went ahead and did so is because synthetic division involves a lot of trial and error. Lots of times things don't work and you just have to live with it and move on. Okay, so as we move on, let me introduce the speedy way of doing this. So remember, we're still stuck with these numbers here. And instead of rewriting them each time, one thing you can learn to do is do synthetic division in one single line. The way I like to do is draw a line under it and then put the number we want to put into it here. Well, we also knew that 3 was a possible rational root. Remember, because 3 was a factor of 36. And so the way we can do it here now is we pull down the 1 as usual, same as above, and then we're going to multiply here. So you're kind of doing this with your eye. Multiply, and then we'll just add, and we'll do that in one move. It can save you some time, and as you get used to synthetic division, you can learn to do this in the one-line method. So 3 times 1 plus negative 10, negative 7. Negative 7 times 3 is negative 21 plus positive 33 is 12. And finally 12 times 3 is 36 plus negative 36 is 0. Aha! It worked. So that means 3 is a root. In other words, 3 is a winner. 3 is a root. All right, so our roots so far that we've discovered are 1 and 3. Now, let's look at our quotient this time. Again, and I'm going to change color to make the point here. What's left over here, right? These 3 coefficients are the quotient. And it's always 1 degree less than what we started with. So we started with 4 terms, that's 3 degrees. Now we have 3 terms, so that's a second degree equation. We could just go ahead and write it then as, again, there's the 1 coefficient for x squared minus 7 times x plus 12, right? So that is the leftover quotient. And at this point, look, I'm going to get rid of that 1. This is just a simple quadratic. Again, we're essentially saying let's set it equal to 0, and we could just factor at this point. I think that'll be a lot easier than continuing to do synthetic division. All right, so that's how we factor x minus 3 times x plus x minus 4. And so our last 2 roots are 3 and 4. Now notice, 3 showed up again. Aha, we had 3 here, we have 3 here. And when that happens, that is called a double root. And we'll see what that means in the picture in just a minute. A double root. Okay, so there you have it. We have all of our roots. I'll go back to orange and write them here. 3 and 4. Now, what is the sum of those numbers? Well, 1 plus 3 plus 4 is 11. What's the product of those numbers? 1 times 3 times 3 times 4 is 12 times 3, 36. And in fact, we'll turn back real quick. That is what we had for our prediction. We had an 11 here for the sum and a 36 here for the product. It's not really a prediction. It's always going to be the case. Okay, so lastly, let's just sort of sum everything up and take a look at what this graph actually looks like. Go back to magenta, our favorite color. We'll put our y-axis there and our x-axis here, and let's think about it. So we knew that this thing opened up like a W. It's going to open up on both ends, and now we know some more. We know that 1 is a root, so we want to point there. We know that 2 is not. We notice that. We know that 3 is a double root. Now, a double root means that it's just going to touch the graph here at 3. All right? It's just going to touch it and glance off and sort of bounce off. And we also knew that 4 was a root. We know that if you just plug in 0 for x, our y-intercept is 36, so way up here, right? So we're going to come from way up here, and then we know that, not quite like that, we're going to come from way up here, and we know that we're going to go through 1, right? So that's the first thing we know. And now we're underneath, all right? And we know that 3 is a double root. So what a double root means is you might come down and then just glance off the 3 and then go back, and then we got to go through 4, so we better turn around. And there's our W, right? There's our W. We're opening up in both directions, and voila, there you have it. We have graphed a 4th degree equation, which looks here like a W. We found the roots 1, 3, 3, and 4 using synthetic division. We've confirmed the formulas for the sum of the roots and the product of the roots. We used the rational root theorem to sort of predict which roots or which numbers we wanted to try when using synthetic division. And we have a nice little W here as our final product. Okay, that's all for now. As always, thank you for watching, and I will see you in the future.